Good morning. Good morning. Welcome to our extra class on Saturday. Today, I would like to introduce many new, perhaps not very new to you, but very interesting as well as very important concepts regarding AC circuits, which you would be using throughout your life. Okay. So, in the previous class, what we discussed was about AC circuit, AC fundamentals. Plus, we also discussed about one AC circuit, that is a circuit containing resistance only. I also introduced the concept of phasors, wherein you can represent AC circuits by phasors also. So, many representations were discussed. One was AC quantities can be represented in terms of by drawing their waveforms, or they can be represented by writing their equations, that is small I is equal to Im sine omega t, V is equal to Vm sine omega t, or omega t plus or minus phi, where phi is the phase angle. We discussed about phase angle difference. If it's a sinusoidal wave, we use Im sine omega t, that is the equation. Omega is 2 pi f. Then we also discussed about the third kind of representation by using phasors. Phasors can be used for representing only sinusoidal quantities, as we saw how this kind of a rotation of a phasor can be, the y-axis projection of that phasor can be represented by a sinusoidal wave. So phasors can be used to represent sinusoidal waveforms. And a phase lag or phase lead can be easily shown by using phasor diagram. This is how we discussed in about AC. And then when we went on to AC circuits, where we saw a single resistance or a purely resistive circuit, in which case we found that voltage and current are in phase, which means a waveform of voltage and waveform of current, if you draw, they cross the zero points at the same time or at the same angles, 0, pi, 2 pi, 3 pi, so on. And when you draw the phasor, we have VR, which is the voltage drop across the resistance, and IR, which is the current through the resistance, are in parallel, which means they are having no phase difference. And when we drew the power, or we drew the phase, the voltage, then the current waveform, then we drew the power waveform also, in which we saw that the power is always positive, or power is being consumed by the resistance. And we found out the equation also of average power, which was Vm Im by 2, that we divided it as Vm by root 2 into Im by root 2, or as we had already found out, Vm by root 2 is Vrms, Im by root 2 is Irms. Normally, when you write Rms values, you don't put this suffix at all. So we say that the average power consumed by resistance is P is equal to Vi. And I also asked you to note that the frequency of the power curve is double that of the circuit frequency. It was going with a double frequency. Okay. So when you are asked in a resistive circuit, if the instantaneous values of, let me go to the presentation. This is a problem which you can write down, or if this is a simple thing which I just wanted to mention, that is if it is a purely resistive circuit, okay. And if current is given as I is equal to 250 sine omega t, instead of omega t, I can even put the value there as 314t, and voltage is given as 10. Oh, sorry, this is voltage. Oh, okay, sorry. This is voltage, and this is current. I is equal to 10 sine omega t, that is 314t.
Ma'am, it's not visible.
It's, oh, sorry, I didn't push this button. Present. Sorry. Thank you for reminding me. Okay. So now can you see now?
Yes, ma'am.
Yes, ma'am.
Okay. So if I am considering an R circuit, a purely R circuit, where I am applying a voltage of 250 sine 314t, I is equal to 10 sine 314t, and I'm asked to find out the peak power and average power. This part I'll go very fast because this is what you have already been finding out. Peak power means peak power in a purely resistive circuit will be Vm Im. Here Vm is 250, Im is 10. 250 into 10, 2500 watt. Average power, on the other hand, will be Vi, that is Vm by root 2 into Im by root 2, or I can even write this as Vm Im by 2. In my case, this will be 2500 by 2, 1250 watts. This I could have found out as 250 by root 2 into 10 by root 2, and I'll get the same answer. This is clear, I hope. Now I'm going on to another problem. This is also an easy one. Again, I'm taking a purely resistive circuit, and the resistance is given as, you may write it down along with me, even though I'm going very fast. This purely resistive circuits are very well known to you. That is why I'm going very fast. Okay, the resistance is given as 10 ohm. So it is given as 10 ohm. So 10 ohm is connected across a 230 volt 50 hertz supply. Okay. You are asked to find out the current, power consumed, and equation for I and V. This is the question. Now, why did I put this question? Just to make sure that you understand that this 230 volt which is given is the RMS value. This is the RMS value. Okay. But if any voltage or any current in any problem from here on is given without a specified any specifications, you have to assume or you have to know that those are RMS values. Then how will we find out I? You are asked to find out the current through the circuit. Again, this current that is asked is the RMS value. Okay. So I will be, as you know, V by R, our own Ohm's law. So you have 230 by 10 and you will get 23 amperes. That is covered. Power P, power consumed by asking power consumed, you are asked to find out P average. That is a power consumed. P is equal to VI that we have already found out. This is equal to 230 into 23. 5290 watts. Now you are asked to find out the equation for I and equation for V in a purely resistive circuit, which means I is equal to Im sine omega t. V is equal to Vm sine omega t itself because they are in phase. If I put VR as this and IR as the current passing through it, I know that VR and IR are in phase, Now, if I want Im, I need to take this 23 as a RMS value. So Im will be IRMS into root 2, isn't it? We have already found out that I is equal to Im by root 2 or IRMS is equal to Im by root 2. Now, from now on, I am not going to write that RMS as a suffix, I into root 2. Vm is equal to V into root 2. Okay. I into root 2 will be 23 into root 2, which you will get as 32.52. This naturally 230 into root 2 will be 325.2. So, and then another thing that you want is omega. Omega is equal to 2 pi f. F is given in the question as 50 hertz. Sorry, I forgot to give you that. Okay. Oh, okay. That is given. Okay. 50 hertz. Okay. It is already written there. 50 hertz. So, 2 pi f will be 2 pi into 50. That is 2 pi into 50 will be 340. So, I is equal to 32.52 sine 314t, and V is equal to 325.2 sine 314t. This is how you do this problem. So much regarding pure resistive circuit. Any doubts here, please ask me. Any doubts till now? Till now, in any of the concepts introduced, please ask me. We are going on to the next section. Is that okay? Okay. So we are passing on to the next section where I am considering an AC circuit containing pure inductance, pure inductance or pure inductance only. Okay, which means I will be having an inductance. Inductance, as you know, is represented by a coil like this, and I have a source where V is equal to Vm sine omega t. This is my inductance L, and I have a current I passing through it. Okay. Now, what is the difference between a resistance and an inductance? Any circuit that is capable of producing a flux when current is passed through it is an inductive circuit. Okay. When an alternating current flows through pure inductance, as you know, a back EMF V is equal to L di by dt is produced, is induced actually. And this back EMF at any instant opposes the very cause producing it, our old Lenz's law. Now, which means that you don't have an ohmic drop, a resistive drop is not there, whereas always this inductance, all of you should note this point, this inductance in an AC circuit always opposes the very cause producing it. What is the very cause producing it? The change in current, the current. So what happens is that the inductance always tries to oppose the production of current in it. That is, it will always delay the current which passes through it. If I switch on the supply, suddenly the current will not become its value, its maximum. It takes some time to build up to its maximum value. Inductance in an AC circuit always opposes the buildup of current in the circuit. Okay. Now, let us see what will be the equation for I. In a resistive circuit, we saw that V is equal to Vm sine omega t. And when I applied the Ohm's law to find out I is equal to V by R, etc., we found that in equation for I is equal to Im sine omega t itself. Now, in this case, let's see what is the equation for I. V is equal to Vm sine omega t. Equation number 1, I am taking that V is the reference. Okay. Now, this Vm sine omega t is the same as L di by dt, isn't it? Or di is equal to, I am going to derive the equation for I. Okay. Di is equal to Vm by L sine omega t dt, or I is equal to integral Vm by L sine omega t dt, or d omega, and then that will become Vm by omega L, it is with respect to dt, minus cos omega t, minus cos omega t. This can be written as, which means I can write I is equal to Vm by omega L minus cos omega t, I can write as sine omega t minus pi by 2. I hope all of you will agree with that. So what did I get? I started with a V is equal to Vm sine omega t, and I am getting the equation number 2. Now, when will this I become equal to I max? When I be equal to I max? When sine omega t minus pi by 2 is 1. Or I can rewrite this equation as I is equal to Im, because I max is equal to Vm by omega L, isn't it? When sine omega t minus pi by 2 is 1. So this is Im. Instead of Vm by omega L, I can write Im. Im sine omega t minus pi by 2. So what is it that I got? As I told you, I started with a reference equation V is equal to Vm sine omega t when I supplied such a voltage to a purely inductive circuit. The current through the inductive circuit is given by this equation. I is equal to Im sine omega t minus pi by 2. What does that mean? When the current is lagging, I hope you understood. The current is lagging behind the voltage by an angle pi by 2. Now, if I represent that by means of phasor, that will be like, I will put V as this or VL as this. This is VL. Okay. And where will I get I or IL? IL will be lagging behind VL by exactly 90 degrees because pi by 2. Any doubts here? Please ask me. Did you understand? Albin?
Yes, ma'am.
Okay. So here I represented this quantity by equation as well as phasor. Now the third kind of representation that we were talking about was the waveform. Okay. Suppose I take V, I and power here. How will I get? I will get, suppose in the case of voltage, suppose I draw the voltage as a reference. I have always taken voltage as a reference. So I'm taking this. This is 0, pi, 2 pi. I need pi by 2 as well, isn't it? I need these points as well because when I draw the current is lagging behind. Current is lagging. Current reaches the 0. Voltage has already reached here. Current reaches the 0 only pi by 2 degrees later. So this goes like this, goes like this. This is I, this is V. So omega t of theta. Hope you understood. What we have done is V is equal to Vm sine omega t. I is equal to Im sine omega t minus pi by 2, minus 90. Okay. There is also a physical explanation as to why current is lagging. Current is lagging because I told you in an inductive circuit, the inductance always tries to, according to Lenz's law, inductance always tries to oppose the buildup of current. So the current can increase only after some time, even after you have applied the voltage. So current is always lagging. So one more thing which you have to always remember, current lagging, you say phase lag. Current leading, you say phase lead. All the lag and lead, etc. of the phase is with respect to current. Okay, so in our case, we can say that the current is lagging, and so you can say that in a pure resistive circuit, there is a phase lag of pi by 2. The phase angle lag is pi by 2 in a purely inductive circuit. Okay. And this, because it is not like a purely resistive circuit, we need to introduce a new term which is called as induct. Have you all drawn this?
Yes, ma'am.
Okay. We need to introduce a new term which is called as inductive reactance. Inductive reactance. We don't have a resistance here, so we need some other kind of terminology to represent something. As you know, where we wrote that Im is equal to Vm by omega L while deriving the equation. Okay. So if you note this, instead of Vm and Im, I can always convert this into I is equal to V by omega L, because here if I put a root 2, here again I can put a root 2. That's all. So I am now writing this equation in terms of their RMS values. Voltage and current are RMS values. Don't you see a similarity with respect to V is equal or I is equal? One second. Okay. Now, if I bring it here, V by I is equal to omega L. Okay. So clearly, this omega L, don't you see a similarity with our Ohm's law? V by I is equal to R. Similarly, here I have a omega L coming in. R used to be an opposition in an inductive circuit, in a purely resistive circuit, to the flow of current. So here also omega L should be an opposition to the flow of current. This omega L we note as XL, the inductive reactance, or inductive reactance XL is equal to omega L. Very important. And where omega is again 2 pi F. You always need to remember XL is equal to inductive reactance XL is equal to omega L, which is actually the opposition offered by the inductance to the flow of current. Now we come to one more definition, one more section is there in here in this inductive circuit, which is the power. Power. I didn't mention about the power. So instantaneous power, small p, was equal to Vi. That is how we did in the case of resistive circuit also. So that is equal to Vm sin omega t into Im sin omega t minus pi by 2, or minus of Vm Im sin omega t cos omega t. You should know better than me how to convert this into this form, or minus Vm Im by 2 sin 2 omega t, this quantity. Now, if I find out the average power here over one cycle, what will be the value here? You can see there is a sin 2 omega t. If I find out the average value from the instantaneous value, average value from the instantaneous value means 1 by 2 pi integral 0 to 2 pi of this quantity. What will be that value? If you have a symmetrical wave and you are taking, Sine 2 omega t is also a sine wave. And if you are taking a average value over a full cycle, what will be that value? Someone please respond.
0.
0. 0. Or what does that mean? The power absorbed by or in a pure inductance is 0. Very important. The power absorbed in a pure inductance is 0, which means where does that power go? Anyway, you are having an inductive circuit, you are applying a voltage small v and a current I also flows, then where does that power go? That is indeed a question. Let's see, we'll draw that power curve and then we will understand better. I'm going to erase this. These derivations may be asked also. Okay, if you know all these things, you needn't even study by heart. You can just put in those. Okay. So if I draw the waveforms once again, I will understand what is happening in the curve. So V, if I draw V, so this is V, because V is equal to Vm sine omega t. Then I am going to draw I. I know is I is equal to Im sine omega t minus pi by 2 in an inductive circuit. So I choose these points pi by 2, 2 pi, 3 pi by 2, 4 pi. So my current is lagging, which means my current waveform will be something like this. Okay. Now, how will I have the power waveform? From 0 to pi by 2. Power, as I know, power, instantaneous power I know is V into I. Every point here, I should multiply V and I. From 0 to pi by 2. All of you should listen. I'll give you time to draw. From 0 to pi by 2. Voltage is positive, current is negative, which means I will have a negative power. Okay, this is P. From pi by 2 to 2 pi, from pi by 2 to 2 pi, both voltage and current are positive. So I have a positive power. From 2 pi to 3 pi by 2, current is negative, voltage is positive, which means again I will have a negative power. From 3 pi by 2 to 4 pi, if I consider both of them are negative, both voltage and current are negative, so I will have a positive power. Need not draw it now. Please listen to me. I'll give you time to draw. What I did here was I drew first the voltage waveform. V is equal to Vm sine omega t. Then I drew the current waveform. I is equal to Im sine omega t minus pi by 2, which means I drew the current by shifting it by pi by 2, lagging it by pi by 2. Then I drew the power waveform. Power waveform, checking at all instants how the voltage and current are from 0 to pi by 2. From 0 to pi by 2, I saw that voltage is having positive value, but current is negative, which means the power P is equal to VI will have a negative value. From pi by 2 to 2 pi, you are having both voltage and current as positive values. So naturally power will be positive. And from 2 pi to 3 pi, you can see that the voltage is negative, current is positive. So you will have a negative power. From 3 pi to 4 pi, both voltage and current are negative. So you will have negative into negative is a positive. So you will have power as positive. So this is the power waveform. Now, I will give you time to draw, need not draw now. Whatever I am telling you, please listen. So during the first 90 degree of the cycle, you have positive power. From 90 degrees to 180 degrees, you have, sorry, from 0 to 90 degrees, you have negative power. From 90 to 180 degree, you have positive power. Then again, it's negative and then it becomes positive. Whereas when it was a resistive circuit, if you remember, you always had power like this, always positive power. Which, and we said that the power is equal to power consumed is VI. But in this case, if you look, you have a positive power and a negative power, which means in a full cycle, no power is consumed, which means positive power means from the source, power is supplied to the inductance, and negative power is from the inductance back to the power. How can the inductance store energy? It is being stored in the magnetic field because it's producing flux. So at during one cycle, power is given to set up the magnetic field, and during the next half cycle, that power or that energy, that stored energy in the magnetic field is being supplied back to the source, or energy is being supplied and taken back every time, and no energy is being consumed, no power is consumed in the inductance. Okay, such power is called as a reactive power. The power is supplied to the inductance only to set up a magnetic field, and later on in the same cycle, in the next cycle, what happens is that that energy is supplied back to the source. Okay, so no power is consumed by the inductance, which means that if I manage to have a purely inductive circuit, and there will be no heat produced, there will be no power dissipation. Whereas if it's a purely resistive circuit, heat is produced. V is equal to P is equal to VI, which is the same as I squared R. VI, which is the same as I squared R, if it's a pure resistive circuit. Okay, I hope this is clear to you. Please draw the circuit, draw this waveform. If you have any doubts, please ask. I'll pause for say 1 or 2 minutes. 1 minute. Is the concept clear? If you want me to explain once again, I am okay with it. These concepts are very basics, but these basics you should be very sure about. Should never go wrong in these basics. That's why I'm repeatedly saying these things, these concepts. If you want me to explain once again, I am okay with it. Is that okay, Archa?
Yes, ma'am.
Okay. Now, please write down this. I know it's very, boring to write, but this you have to write. When current rises in an inductor, when current rises in an inductor, when current rises in an inductor, energy is required to build. Energy is required to build a magnetic field around it. Energy is required to build a magnetic field around it. This energy is supplied by the source. This energy is supplied by the source and is stored in the magnetic field of the inductor, and is stored in the magnetic field of the inductor. As the current falls, as the current falls, the collapsing magnetic field returns the stored energy to the source. The collapsing magnetic field returns the stored energy to the source. Okay, so the energy is flowing back and forth. Source in the inductance inductance in the source. Inductance in the inductance in the magnetic field. Okay, no power is consumed. Okay, then a question, a problem, a small problem where you can see all these things coming in. Okay, you have a pure inductance. Instead of putting the problem in words, I'm just drawing this. You have oh God, my over enthusiasm, I drew something else. Okay, so you have a pure inductance, okay, which is connected to a voltage source. It allows a current of purely inductive current coil allows a current of 10 ampere, which means whatever you are given is the RMS value. 10 ampere is allowed to is flown when a 230 volt 50 hertz supply is provided. See, 230 and 10 are both RMS values of voltage and current respectively. Okay, you are asked to find out the inductive reactance. Find the inductive reactance. 2, inductance of the coil. Inductance of the coil. And also power absorbed. 4, equation for voltage and current. Had it been our offline class, I would have given you time to draw. But in online class, I think it's better that I do it. So it's given as, V is given as 230 volts. I is given as 10 ampere. As in the case of a resistive circuit, I know V by I is equal to R in a resistive circuit. But in a purely inductive circuit, V by I is equal to XL. Or I am asked to find out the inductive reactance XL. XL is equal to V by I, that is 230 by 10 is equal to 23 ohm itself. Its unit is ohm, same as that. Okay, XL. Then you are asked to find out L. The XL has another equation. XL is 2 pi f L or omega L. XL is omega L. Omega is 2 pi f. So XL is equal to omega L, that is 2 pi fl, or XL I got as 23 is equal to 2 into pi into, already given it's 50 hertz, 50 into L. The only unknown is L. Therefore, L is equal to 23 by 2 into pi into 50, which you will get as 0.073 because it is inductance, Henry. Unit is Henry. Remember, XL, inductive reactance, is similar to our resistance. Its unit is ohm. And remember, L, the inductance, is having a unit of Henry. Now, the third question. This is done. This is also done. The third question, power absorbed. Tell me the answer, someone.
0.
Huh?
0.
0. Power absorbed is 0. Though that question is asked, remember, it's a purely inductive circuit and power absorbed is 0. Power just flows up, flows towards the inductive magnetic field, it goes back to the source. That's all. No power is absorbed, no power is dissipated, no power is utilized, if I may say so. Then you are asked to find out V and I. V is equal to Vm sine omega t. I is equal to Im sine omega t minus pi by 2. I know you know how to do that. Vm can be found out from V by using that root 2 conversion. Im can be found out from I by using that root 2 conversion because it's a sinusoidal wave. What is that conversion? Vm is equal to root 2 V. Im is equal to root 2 I. Just substitute and write this equation. That is all. That's all. Okay. Hope this much is clear to all of you. Anything, any doubt you have regarding the portions that we dealt with today, please ask me. Okay. Now I will give you a break, not now, after considering a C circuit also, a purely capacitive circuit in similar lines, same as this. Let's see what is happening there. Okay. Now let me and then we'll have a break. Okay. So AC circuit containing pure capacitance only, or if I draw the wave circuit, I'll have only a pure capacitance. AC source. Now, in the case of an inductor, I was talking about a magnetic field produced. The energy that is supplied by the source is utilized to produce a magnetic field around the inductance. In the case of capacitance, the whatever energy is supplied by the source is used to produce an electrostatic field across the plates of the capacitor. Electrostatic field across the across the plates of the capacitor. Let's see how that works out. Okay, so V is equal to, again as before, we'll be putting this. V is equal to Vm sine omega t, and I will be finding out the equation for I and checking whether there is a phase difference at all. How will I proceed? So I will again start with V is equal to Vm sine omega t. In the previous case, what did we do? V was written in terms of L and di by dt. V is equal to L di by dt. That was the equation relevant for an inductance. In the case of a resistance circuit, we used Ohm's law. V is equal to IR. That Ohm's law was put into use to find out I. I is equal to V by R. Similarly, we have to find out the relevant equation by which we can get the equation for I here. So we usually find out in the case of capacitance, we are more concerned with charge. So Q is equal to CV, that we know, or that is equal to C into capacitance C into small v, Vm sine omega t. Now we cannot restrict our discussion to Q. Instead, we want I, or the circuit current I is equal to dq by dt, or I can put this as d by dt of C Vm sine omega t, or I is equal to, I am differentiating and taking all those values out, omega C into Vm cos omega t. That is equal to omega C Vm. Instead of cos omega t, I want it in terms of sine. So sine omega t plus pi by 2. Omega t plus pi by 2. And as you know, I becomes I max when sine omega t plus pi by 2 is 1. Or I can rewrite this equation as I is equal to, this is Im sine omega t plus pi by 2. Or what I understand is that in a purely capacitive circuit, if I give a supply voltage as V is equal to Vm sin omega t, I end up with the current through the circuit or through the capacitance as I is equal to Im sin omega t plus pi by 2, or the current is leading. Current leads, the phase angle current leads by pi by 2. Or if I draw the phasor as this as Vc, that is the voltage across the capacitance, IC would be 90 degrees ahead. IC, exactly 90 degrees ahead. This is how I can draw the phasor diagram. I hope this is clear. Which means I have a new term coming here. Okay. That is, here I got, instead of our inductive reactance, obviously I got a new term coming here. I got Im is equal to omega C Vm. Or if I put root 2 here, I can write I RMS is equal to omega C V RMS. Okay. Now, if I bring it in the form of my already familiar, Ohm's law, I get it as V by I is equal to 1 by omega C, where I put that 1 by omega C as Xc, the capacitive reactance. Capacitive reactance. Or Xc is equal to 1 by omega C. Remember, on the other hand, XL was omega L itself. Remember, when it comes to Xc, it is 1 by omega C. Don't go wrong. This is called as capacitive reactance. Now, one more portion and then this is over. Coming to our power. Okay. I hope all of you are writing it down along with me. Then coming to the section where we are dealing with power. We want to know how the power varies. So, I have the theta or omega t here. And then if I draw the voltage like this, again I'm taking voltage as a reference. So, I'm drawing voltage here as V. I will be leading, isn't it? So I leading by pi by 2 means I have current I has already become, already passed the 0 point pi by 2 before, which means the current now it is coming like this and it has passed through. So pi by 2, 3 pi by 2, 0 pi 2 pi. So current waveform will be like this. Okay. This is I. This is leading. Current is leading because V is equal to Vm sin omega t. I is equal to Im sin omega t plus pi by 2 in the case of capacitance. Now if I am drawing the power waveform from 0 to pi by 2, both I and V are positive, so I have a positive power. P. From pi by 2 to pi, voltage is positive, current is negative, so I have a negative power. From pi to 3 pi by 2, both current and voltage are negative. So I should have negative into negative will be positive. How do I get that? Because I know at every point instantaneous power is V into I. Then from here to here, again negative. When you draw, please try to draw to scale. So this is your power curve. This is your power curve. As in the previous case, you will see that when voltage rises, there it was current rises. Okay. Here it's voltage, or you can write this. Please write down this. I'll give you time to draw also. Please write down this. When voltage rises, across the plates of the capacitor, when voltage rises across the plates of the capacitor, energy is required to build up electrostatic field, not the electromagnetic field as in the case of inductance. This is electrostatic field between the plates of the capacitor. This energy is supplied by the source and stored in the electrostatic field. This energy is supplied by the source and stored in the electrostatic field of the capacitor. As the voltage falls, the collapsing electrostatic field returns the stored energy to the source. Which means that even from the power curve, which means that you're having energy supplied by the source towards the capacitance electrostatic field. Then at the other, from pi by t to pi, it is negative power. Negative power means the power is being supplied back to the source, which means energy is flowing back and forth. Again, as in the previous case, if I derive the equation, did you draw those figures? Varsha?
Yes.
Okay. So if I derive the equation as in the previous case, P is equal to VI, I should get the average power as 0, isn't it? So V is equal to Vm sine omega t into Im sine omega t plus pi by 2. So as in the previous case, I can write Vm Im sine omega t into sine omega t plus pi by 2. I can write as sine omega t cos omega t, or Vm Im by 2 sine 2 omega t. Whenever I find that there is a sine term or a cosine term, I know it's a symmetrical wave. Again, average power will be 0 over a whole cycle. That I know. But again, just to show that over a whole cycle, 0 to 2 pi of this quantity, Vm Im by 2 sine 2 omega t with a base of 1 by 2 pi will be equal to 0. So again, power absorbed, that is the underlying point here. Power absorbed or dissipated or utilized in a pure capacitance is 0. So the underlying point is, if you have a circuit having a resistance, an inductance and a capacitance, and you are giving some supply to it, the element which consumes power is only resistance. That we'll come to in a later stage. Neither the inductance nor the capacitance has any role in consuming the resistance. Some problems we can do in this section after a break. Now it's 10:33. We'll meet back at 10:45. You'll get enough time. 15 minutes break. Okay, is that okay? If you have any doubts, please remain and ask me, or you can ask me now. I'll wait for a few minutes too.